All right, everybody, let's look at case 2 for the partial fraction decomposition. Case 2 is involving where q has repeated linear factors. And so this is like if you have x minus a to the n, so for instance, x minus 3 cubed, even x cubed or x squared, because the 0 is still going to be the number 0. And so anytime it has a repeated linear factor, when n is something greater than or equal to 2, then your partial fraction decomposition would be set up like a sub 1 over x minus a sub 1. And sorry, we don't need the a sub 1 here, it's just x minus a, because that's the factor. And then it's going to be a sub 2 x minus a sub squared, x minus a quantity squared. And so what you're seeing is happening is if n is 2, this would be how we would set up the partial fraction decomposition. If n is 3, we would have a sub 3 over x minus a cubed. And so since n is n, we'll have plus dot 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 plus a sub n over x minus a to the n. So you're going to start with, you're basically going to have n factors here. So if you have, if your n is 4, there's going to be x minus a to the second, x minus a to the third, x minus a to the fourth. And often on top, I'll just leave this as a, b, c, d, instead of keeping track of all the subscripts. All right, so, and also just a note, let me just write this now. If you have x to the n, it's still going to be in this form because it's a repeated linear factor, because this is the same as x minus 0 to the n, where a is 0. So make sure you keep note of that. All right, so for our problem we're going to look at, we already have the denominator factored, that's super, but this also throws back to chapter 3 when if we were given a polynomial that was not in factored form, we now have the skills to write it in that factored form. All right, so we're going to set up our partial fraction decomposition by expressing this as, so this first factor is the repeated linear factor. This means I'm going to have a over x minus 1 plus b over x minus 1 squared. So this is the partial fraction decomposition just set up for the factor x minus 1 squared. The next one is a linear factor that's non-repeated. And so it's just going to be like we saw from case 1, in which case it's plus c over x plus 1. And so, again, if this had been, well, let's take a step back. If this had been x minus 1 to the third, for instance, you would want to have plus c over x minus 1 to the third. So you're just going to keep going until you reach that exponent. Since it's not, we're just going to the next linear factor that we have, which is the non-repeated. So we're going to say plus, let's go back to the black, we'll go, so it'll be plus c over x plus 1. All right, and again, we're going to make all the denominators the same. And so in this case, we can multiply this by another x minus 1 on the top and bottom. And it also needs x plus 1. The middle term is missing the factor x plus 1. And the last term is missing the factor x minus 1 squared. And now that all the denominators are the same, the denominator is canceled, and I'm going to distribute and clean up on the top and eventually equate my coefficients. So I'll be left with x squared, and again I'm going to write this as x squared plus 0x plus 0, because I want to be able to make sure that everything that's on the left is going to be exactly the same as on the right. This is going to be, well, this is going to multiply to x squared minus 1 and then times that by a, so we'll have a x squared minus a, and plus bx plus b, and plus, this multiplies to x squared minus 2x plus 1, and then times that by c, so cx squared minus 2cx plus c. Okay, so from here, I want to group the x squareds, the x's, and the constants. So I'm going to be left with x squared plus my 0x plus 0 equaling a plus b times x, oops, sorry, not plus b, it's plus c. So ax squared plus cx squared, so you can factor out the x squared. Now looking at the bx's, or just the x's, so I can write this as b minus 2cx. And then my constant is going to be negative a, let's see, plus b plus c. And here's the cool part with this, why I like this approach, is that you're saying that this left side is equal to this right side. In order for that to be the case, a plus c needs to equal 1. And then 0 has to equal b minus 2c. And this doesn't look like a c. So 0 has to equal b minus 2c. And lastly, let's write it over here, 0 will equal negative a plus b plus c. And so now we have the system of linear equations, so we can solve for a, b, and c.